welcome to lecture 4, part 3. What we've done so far is we've shown how to generate, in this pseudo sense, random numbers. Remember, random numbers here, these are uniform 0, 1 variables. That's our definition in simulation. Now we want to show how do we take these random numbers and generate random variables. So any random variable. Well, we're going to start off with that as the cumulative distribution function. And then we're going to take advantage of the fact that both of these things are between 0 and 1, the random numbers and the CDF. And we're going to use something called the inverse transform method to transform the random number into the random variable for a given CDF. See how that works. So we're going to start with an example. We're going to use a discrete random variable first for our examples. And it has this CDF here. Recall that this CDF means like fx of a is the probability that x is less than or equal to a. And from this idea and examining what we have here, we can see that, well, the probability that it's less than or equal to, say, 1 is 0, 1.9 is 0, 1.99 is 0. As close as you want to get to 2, the probability that x is less than or equal to that is 0 until you get to 2, at which point suddenly the probability that it's less than or equal to 2 is 0.3. But that's true for values higher than 2 until you get to 4, which means that x can assume the value of 2. Similarly, you can make the same argument that it can only assume the values 2, 4, and 7. If that's not clear to you, you should try to convince yourself of that. And if you still have questions, come and talk to me. I can show you the math of that. Okay, so what is the probability that x is actually equal to 4? Well, to calculate that, we're going to use the probability that a is in this interval. Remember, we saw this in the probability review. That's equal to fx of b minus fx of a. Okay, so the probability that px of 4, which is the probability that x equals 4, that's going to be the probability that x is less than or equal to 4 minus the probability that x is less than or equal to 2, which is equal to 0.8 minus 0.3, which is equal to 0.5. Okay. Similarly, the probability that x is equal to 2 is 0.3, and the probability that x is equal to 7 is 0.2. So if we can generate a lot of random numbers, the percentage of them that will correspond to the interval corresponding to x equals 4 is just 50% of them. Okay. So we're going to split up the interval from 0 to 1 for this discrete random, and where the uniform variable lies in there, what this random number lies in, is going to correspond to what number we return for x. Okay, so what we do is we generate we have our random variable with these different values for the discrete case, and we basically calculate out the different probabilities that the sort of the region of 0, 1, we divide it into such a case so that in the following way, we just use this CDF to divide it up into regions. And then depending on what region the uniform random variable lies in, what region the random number lies in, we use that region and return that value for the random variable x. Okay. So let's just go back to this example just to illustrate it one more time. So if the uniform random variable, in other words, the random number, if we generate it and it's between 0 and 0.3, then we return x equals 2. If it comes out so that it's 0.3 to 0.8, we return 4. If it's between 0.8 and 1, we return 7. Okay, well, what about the continuous case? Well, remember this gets at our paradox of, the probability that it's any one particular value is 0, so you have to think about regions, and you might think, well, how does that work? Because we're still going to have to generate particular values for continuous random variables, and you might think of the simulation we just wrote in Simio where you had an exponential random variable and you had a gamma random variable. And how is that working? Well, it turns out what we can do is we can take the inverse of the CDF. And if we set x equal to the inverse evaluated at u, we actually get the right thing. And why does this work? Well, the probability that x is less than or equal to a, that's equal to the probability that f inverse of x of u is less than or equal to a, right? Because of this relationship, that's just substitution. That's equal to the probability that f of x, if we apply that to both sides, of f inverse of u is less than or equal to f of x of a. This is just applying f of x to both sides. Well, this is just the probability that u is less than or equal to fx of a. And remember, well, what is that? That's just equal to fx of a by the properties of the uniform 0, 1. If that last step is a little confusing for you, you might want to check out the probability review. If it's still confusing you, please let me know and I can try to answer your questions. So because of the uniqueness of the CDF for x, in other words, we've shown that this method of generating a random variable is going to have the same cumulative distribution function as this unique f of x of a. It means that that is indeed has the same distribution as x. So that method will work. So now we know how to take inverses. So now if we have the CDF and we can closed form solve for the inverse, we now have a generator for x. So let's see the algorithm for that. We're going to generate our random number u. We stick it into the inverse function, and then we output x, a random variable. So let's try it for the following CDF as an example. If we have this as our CDF, it's the square. F of x of a is the squares. In other words, that the probability that x is less than or equal to a equals a squared for 0 less than or equal to a less than 1, right? Because that's fx of a. Remember, this is one of the fundamental definition of CDF. To find the inverse, we basically set a variable, in this case, say b, equal to fx of a, which is equal to a squared, and then we solve for a. And so now, and that will give us our inverse. So this is something you've seen in calculus and in classes before that, I would imagine. So now we know the inverse of fx of inverse is just equal to the square root for 0 less than or equal to b less than or equal to 1. And remember, you have to solve for the right bounds by substituting in you have to substitute the inverse in there as well. But fortunately, when you substitute in the square root of b for a here, you get the same, so you have to square both sides, 0 and 1. You would get back 0 less than or equal to b less than or equal to 1. And so the random variable generator for such a random variable is just x is equal to the square root of u, where u is a uniform 0, 1. In other words, a random number.